one piece of chalk every single class. One day he went, yeah, just writing. He will never go to class without breaking a piece of chalk, and it's all like, it just happens. So one day he made it to a whole class of writing on the board without breaking the chalk, and we're like, wait, this is not normal. Oh yeah, that's right. So he just snapped the chalk in half. But that was the only day he went through a whole class of writing and didn't break the chalk once.
Well, anyway, I don't like the chalkboards, but
I don't like writing.
It's the dust.
it is the dust, yeah.
If there wasn't a dust, I think.
Yeah, I wouldn't have any problem if it were not for the dust. But
I mean, that right there, I want to clean up this desk right here.
yeah,
the table in front is.
unfortunately, the classroom. Let us just finish the chapter, guys. So this is where we were in last class. The statue before and after restoration. And we know that the rainfall, high acidity rainfall, caused that deterioration of the statue. Now, there are things being done to remove the sulfur dioxide from furnaces and wherever you burn coal and other fuel. So this is just a schematic of how an industry, let's say somebody is using a coal furnace, how they can remove or they can reduce the amount of sulfur dioxide they are producing. So what happens is, let's say here your coal, this is your general supply and it's burning and it produces sulfur dioxide. What you do is, through another outlet, you inject powdered limestone or calcium carbonate, which is limestone. And calcium carbonate, you know that calcium carbonate, when you heat it, it decomposes to calcium oxide and carbon dioxide. So the calcium oxide will pick up the sulfur dioxide, which came from the coal burning, and it makes calcium sulfide. Okay, and the calcium sulfide and any leftover sulfur dioxide then will go through another area called the sulfur dioxide scrubber. What you have here is a slurry of calcium oxide and water. So any leftover sulfur dioxide will, the slurry of calcium oxide and water will pick up any leftover sulfur dioxide, so you get all calcium sulfate slurry. So this will remove most of the sulfur dioxide from the furnace. So you can imagine if it's a big industrial plant where they are burning coals all the time in huge amount, this would actually take care of sulfur dioxide, right? So their emissions will not have any sulfur dioxide, but just the carbon dioxide and whatever vapor they have left with. So yeah, as it says, the calcium oxide will react with the sulfur dioxide to form the precipitate of calcium sulfide as a slurry, and then you just remove that. Right now this happens only in big industries, Still we make a lot of sulfur dioxide and send it to the atmosphere, which is not good. Now another culprit is carbon monoxide, and we all heard about carbon monoxide poisoning, right? So the left side picture, this shows red blood cells, or typically hemoglobin in red blood cells, and the heme molecule in red blood cells, it has this structure, that is 4 nitrogens and an iron sitting in the middle, and this iron will bond with one O2 molecule. So this shows the O2 molecule, okay? And then this hemoglobin is a large multi-folded protein, so it has 4 sites like that. So each hemoglobin will take up 4 oxygen molecules and carry through the blood, and wherever cells need oxygen, it would detach the oxygen, and then it will pick up the carbon dioxide and bring it back. That is the normal circulation, right? Now what happens is, if you get exposed to carbon monoxide also has a linear structure like O2, 1 carbon and 1 oxygen. It's a triple bond, right? Now if you remember from previous semester, I need a piece of chalk. Okay, if you remember of carbon monoxide structure, a triple bond, linear structure, lone pair of electrons on carbon and oxygen, that is carbon monoxide, right? Now if you think about the oxygen structure, or double bond, and each oxygen has 2 pairs of lone pairs on it. Now if you look at this picture, you can see that O2 is bonded to iron kind of a bent fashion, not like a straight fashion. That is because of the 2 lone pairs present on each oxygen. So if you think about the geometry, this is like trigonal planar geometry, right? So it's kind of this one electron pair, either this or this, will be attaching to the iron. So because of the trigonal planar geometry, it's going to be that bend shape. Now when it comes to carbon monoxide, it has only 1 lone pair and it's a linear molecule. The geometry there is linear, so it will attach straight, right? Now the iron or the heme molecule will prefer the straight attachment compared to this linear trigonal planar attachment. Now heme molecule doesn't know whether it is oxygen or carbon monoxide. Whatever is there to attach, it would prefer whichever is chemically easy for it, right? So because of the structural difference, the equilibrium constant for carbon monoxide attachment to this heme molecule is almost 200 times greater than oxygen attachment. So if you have carbon monoxide available, heme molecule will preferentially go for carbon monoxide. So each heme molecule which is going for carbon monoxide, that means within our body we are not getting that oxygen wherever it is needed, right? So within some time, body cells are not getting oxygen where it is needed, especially the brain cells and heart muscles and all that, and death can occur, or you will pass out, and then still if you don't get help, then you will die eventually. And this comes so fast because carbon monoxide is colorless and odorless. You have no idea you are breathing that in. You cannot detect, oh, I'm breathing carbon monoxide, so I should go out, right? Once you pass out, then only you know that, I mean, not you, whoever is standing next to you may realize that, oh, okay, something is wrong, and it could be because of carbon monoxide poisoning. So that is why carbon monoxide poisoning comes so fast. Now, because of this reason, products that contain carbon monoxide need good warning systems, and oh, they don't have anything. I think in your book you have a picture of, what is that, kerosene lamp, old-fashioned. So those things, if you look for, they will have clear warnings, because carbon monoxide is produced usually in incomplete burn, and that is why when we have inside furnaces, wood stoves and all that, which we burn things, wood, but it's not a complete burn, right? So carbon monoxide is produced, and that is why we need to have a carbon monoxide alarm or system inside the house where you have a furnace or stove or things like that, because you will never know. It might build up and it might be harmful to you. Now the next atmospheric gas mixture is oxides of nitrogen. This famous picture is the Los Angeles, the smog, photochemical smog in Los Angeles. We know that Los Angeles is one of the most polluted cities, right? I mean, air pollution wise. So this brownish gas that hangs above large cities is primarily nitrogen dioxide, NO2. You saw nitrogen dioxide in today's lab also. Remember when you put the copper in nitric acid, you saw the brown gas, it's the same brown gas. So you can imagine that is toxic, and in a city, if it is hanging there like that, how bad that is to the people who are living in there, right? Now, how this is formed is usually from the oxidation of nitrogen monoxide, which is an exhaust component. Mostly cars would exhaust nitrogen monoxide. And when nitrogen monoxide is in the air, that will react with oxygen from air and makes nitrogen dioxide. And the smog is basically a mixture of mostly nitrogen dioxide and some of the nitrogen monoxide. And the photochemical smog, we call it as photochemical smog, these nitrogen oxides. Here you have a picture, the table given here for the national emission standards. As you can see, Californian standards are given in parentheses, and from 1995 up to 95, I think Californian, nitrogen oxide standards are much stringent in California from 75 onwards. The hydrocarbon standards, at least from 95 onwards, they are lesser than the other national average or the other areas of the country. If the standard is, let's say, 0.075 for hydrocarbon, they can have only 0.05. So carbon monoxide, hydrocarbons, and some ozone also, this mixture along with the oxides of nitrogen, that creates that brown stagnant air mass which stays over large cities, and that is really causing a lot of respiratory problems for people. So as a result, emission standards are getting more and more stringent. Now we will look into water vapor and carbon dioxide. These two gases, which are usually called the greenhouse gases, they act like an insulating blanket on Earth's atmosphere. If you think about Earth, why life is possible on Earth, as we said, when we talked about the atmosphere, we said because of Earth's atmosphere, life is possible. Otherwise, if you just look at Earth compared to other planets, Earth would be too cold for anything to live. Okay? So, because Earth receives energy from sun and then it emits back most of that energy into the atmosphere. Now, if we didn't have an atmosphere, it will be energy coming in, energy going. So, net energy, it will be nothing on Earth's surface. Or, as the book says, the average temperature of Earth would be 254 kelvins, which is below 0 degrees Celsius, right? So life wouldn't be possible. So why Earth has this specific, kind of stable temperature? It's because of its atmosphere, mainly because of the water vapor and carbon dioxide in the atmosphere. What it does is, as it shows, this is the typical picture. That is, if let's assume we don't have this atmosphere here, okay? Then the sunlight energy comes in, and Earth is radiating the energy back as infrared radiation or in the form of heat, and that is just lost to the space. But since we have this atmosphere which is protecting Earth, mainly water vapor and carbon dioxide, what they do is they would return back, or they would again send that infrared radiation back to Earth as heat. So we have that heat always not escaping Earth's atmosphere. As you can see, this is the wavelength, this is the range of wavelength usually emitted by Earth's surface, and wavelength absorbed by carbon dioxide and water. They cover most of it, as you can see. So they again send it back to Earth's surface. Or in other words, this infrared radiation, the heat, this is not, most of it is not escaping Earth's surface. So we have a constant heat blanket above Earth, and therefore life is possible. Now, this blanketing effect is generally known as greenhouse effect, and this would explain, let me see, yeah, with water vapor is the main reason for this blanketing effect. Water vapor has a high specific heat, and it has, as you know, it has the good hydrogen bonding, therefore high melting point, high boiling point, all that. Now, what water vapor does is, now you can kind of understand why we feel more hot in humid days, or humid areas are like, why it's so hot when it is humid, because so much water vapor. So more of that Earth's radiation, the infrared radiation, is being sent back to Earth as heat. So we feel more heat. Now, in desert places where there is no humidity or very low humidity, in the daytime it's very hot because the sun's energy is directly hitting, no filtration by the atmosphere, all rays are hitting the desert. In the night, what happens is, in the desert it becomes very cold because there is no sun hitting in the night, so it's not receiving any energy, but Earth is emitting those infrared radiation, but no water vapor about to send it back, so it is lost to the atmosphere. So it will be very cold during the night. That's what happens in deserts. Now that explains, as I said, in the night time why our Earth is not getting very cold, because we are not receiving any energy during the night time, right, from the sun. But why we are not going, I mean, of course our climate is different, the winter months and going 0 degree, that is not what we are talking about. Overall, overall if you think about Earth's thermal consistency, why Earth doesn't go in the night, everyone goes below 0 degrees, because we have humidity, and humid areas will keep the heat in, the infrared radiation, they will prevent the radiation getting out of the atmosphere to the space, so that heat is stored. Now, carbon monoxide, it helps doing this good thing, but increased levels of carbon monoxide is actually doing a little bit harm to us. We have studies done for over thousands of years, not studies done for thousands of years, what I mean to say is studies which is done on carbon dioxide concentration on air for thousands of years, and we have seen that recently, like let's say last 300 years or so, when we started these large industrial processes, the carbon monoxide concentration has been increased so rapidly, and that is actually it's completely stopping all that infrared radiation going out and putting all the heat back to Earth. But that is a little bit too much for us. Some areas are getting a little bit too warm, or more heat than we needed. That is what is causing that overall so-called global warming. So, and it is happening only this last 300 or so years, when the human activity is creating a lot of carbon dioxide. When the carbon dioxide was created by the natural processes, or whatever the ratio of carbon dioxide was in air through natural, it was fine. Environment was perfectly good. We had a system which was working. But when we started putting so much carbon dioxide, dumping so much carbon dioxide into the environment, then we are making it a little too warm. We are heating the Earth a little too warm. or in other words, we are protecting all that infrared radiation a little too much. We don't need that much. So as you can see, last 50 years, you can see the carbon monoxide concentration in ppm in air from the Mauna Loa Observatory Hawaii lab. It's from 58 to 2008. Last 50 years. See the steady increase. Right? So I guess all those global warming calls. Okay, now just we will look into oceans. Again, oceans, when we talk about, even though we identify 3 major oceans and then so many smaller oceans and all that, we know that all those oceans are connected, right? If you look in the map also, it's all connected. It's one single water body. So as the oceanographers called it, it's the world ocean. The entire ocean, the body, the mass of water. Now, the ocean contains a lot of important compounds and minerals, but we are not going to use it to extract all those products we need. Mainly we use ocean water for only sodium chloride, bromine and magnesium. Those are the 3 things we directly extract from seawater. Now, how do we extract things from seawater, or how do we purify seawater? This process is called desalination. So that famous, I don't know who said that. Who said this? Water, water everywhere and not a drop to drink. Yes, Ryan said that?
Yes.
Okay, we will call it Ryan's statement. So, what? It's from where?
It's from the poem called America.
Ah, okay. Yeah, I've heard this so many times, but I don't know the history of it. So yeah, that is true. I mean, if you are lost in the sea and if you run out of your drinking water, yeah, you see water everywhere, but you cannot drink it because it's too salty, right? It is too salty. The NaCl concentration is too much. So you have to do desalination. Now, how do we do desalination? Or this process is called reverse osmosis. Recall when we learned about colligative properties, we learned about osmosis. And osmosis, usually what happens is water from the dilute region will move to the concentrated region, right? But if you stop the pressure and if you add more pressure, you can actually reverse that process. So now water from the concentrated region is going to move to the diluted region. So now if you think about it, this desalination plants are like huge rooms where you have this big pipes. Inside each of those pipes you have so many hollow fibers of semi-permeable membrane, and what you do is you pass water from one end at a high pressure and the water will keep pumping through these pipes and you collect it at the end. What you are collecting at the other end would be pure water. And what happens in one of these nanotube, this is what will happen. So inside you have the pure water, outside you have the sea water with the water molecules and all the other solute particles, mainly NaCl and other sulfides and bromides and carbonates and all that stuff. Okay. Now what happens is it's the reverse. I mean, if it was natural osmosis, what happens is water from here, it would go here, right? But now it's the reverse osmosis process, so the water molecules from outside will enter to inside, and this membrane is semi-permeable, so those solute particles are not coming along with the water. So you will get the hard solute particles, they just keep concentrating on outside, but inside you have only water molecules, so you start collecting that. So that is the reverse osmosis process. And there are some countries who use this process for making their drinking water. United States is so fortunate that we have a large supply of fresh water and we have a large reservoirs of fresh water, mainly our Great Lakes. They are like all, it's this freshwater lakes, such large reservoirs. Nowhere else in the country, nobody is that fortunate to have such large reservoirs of fresh water. So there are countries who use this reverse osmosis process and desalination plants to make their drinking water. So as I said, water naturally will flow through the semi-permeable membrane from regions of high concentration to low concentration. But if you apply enough pressure, then it can be forced the other way. So it will be going in the opposite direction, where the pure water, from this area, the pure water will be coming inside, and you can collect that. Now, when we talk about the municipal water, the water which we get through our town supply, it's just only a general, each town might have, based on their water supply, the quality, they might have different process or specific measures to take care of it, but this is kind of a general schematic. When municipal towns, when they clean water, what is going on? What they do is, usually they take the water from, let's say, an industry who already has cleaned the water. They take it again, or from a water intake, whatever is their source, and first it goes through a coarse filtration just to remove whatever solid particles in the water. And then this water is let to stand in this huge settling tanks. And when they are, as the name suggests, settling tanks, whatever small sediments in the water, they should slowly settle down to the bottom. And then mostly you will add calcium oxide and aluminum sulfate also to water to make it slightly basic. And when you are added aluminum sulfide, it forms that aluminum hydroxide slurry. It's kind of a precipitate which is in a slurry form. And when that settles, it kinds of, if it is very fine particle which is not sedimenting, then those aluminum hydroxide, when that settles, that kinds of trap those particles in that slurry, and that settle down. So once it is settled down, you collect the clear water and then filter it through a sand filter. And once it is sand filtered, you do a process called aeration. Just you are aerating the water, and then chlorine is added to disinfect. Ozone can also be added to disinfect, but the disadvantage is you have to make ozone where you need to disinfect. So you need something else, some other facility there to create ozone. But chlorine you can store in a tank and you can take to whichever facility you are doing this. You don't have to be creating right there. So mostly chlorine is what is used for disinfecting. Now when you add chlorine gas itself is not doing anything. What happens is, when chlorine gas reacts with water, it produces hypochlorous acid. The acid is what is doing the disinfecting. That would kill the bacteria and viruses or whatever stuff in the water. And that is how we get this water from the town, which is purified. The only disadvantage is it would smell like chlorine, right? Otherwise it is good. So that's just the process again, going through. Water is aerated to increase the amount of dissolved oxygen and promote the oxidation of any organic impurities. And then, as I said, ozone or chlorine, but mostly chlorine. So to the last part, what do we call green chemistry? What do we mean by green chemistry? So the bottom line is that the last 30-40 years we have become really aware of what are we doing to the environment. What is all these industrial revolutions, all these developing nations, all the developments we are doing, but actually what are we doing to the environment? We have become aware of it. Now we want to stop ruining the environment. So when we take measures to do that, that entire area is called the green chemistry, supporting the environment. So promoting chemical processes that are environmentally friendly, that is what is called the green chemistry area. And there are certain principles the green chemist would follow. So rather than worrying about how do we dispose a waste properly, let us think about how can we do this process without creating any waste. Wouldn't that be better than worrying about how do I dispose the waste properly without having anything, right? If you don't have the waste to start with, you don't have to worry about how to dispose it. So that is the first concept. Think about new process or new methods to do the same thing, but creating less waste or no waste at all. That is the first policy. Then, in case if you have to create the waste, then let us think about creating a waste that is non-toxic. That makes sense, right? And the third principle is be energy conscious and energy efficient when you design syntheses. Energy, we would say, we are all aware of all that fossil fuel limitations. People talking about we already crossed the peak or we haven't. I don't know. That discussion again is keep going. So when we design new process, think about the green fuel, like the wind power or what else? What else is solar? The hydrogen fuel, yeah. Yeah.
Yes, it's much worse than gasoline. Hydrogen has to be stored under pressure.
Yes, it is. And that is the main disadvantage why the hydrogen cars are not coming out that cool. I mean, when they came up with the concept, the fuel cell concept, everyone was like, oh my, within 5 years, we are all going to have fuel cell run cars and we are going to be safe. But then they realized you have to store a bomb in your car to drive that car, and people are not ready to take that risk. Sorry, first my life, then only I'm thinking about coming generations, right? That's what everyone is saying.
Well, there's a couple of biomedical companies that have come up with they re-engineered bacteria to make fuel like switchgrass.
Mm-hmm.
Cheap, easy stuff. It's like ethanol is a waste of time.
Yeah, exactly.
They shouldn't spend any money.
I know.
Well, it takes more energy to produce the ethanol than that.
Than how much ethanol you can produce,
You
yeah.
can't burn it in a modern gasoline engine without destroying the engine. 10% is even too high. And but like the switchgrass stuff is comparable to gasoline in terms of its burning temperature, so you can pump it directly into modern engines. So you don't have to change the millions of cars already on the road.
Yeah.
Because a lot of people aren't going to be able to buy a brand
Exactly.
new car.
Yeah.
They could just pump the same fuel in.
Yeah.
It would be different.
A different fuel, yeah.
Maybe effectively the same, just without all the same byproducts.
Exactly. I mean, that is the ultimate goal.
Plus, we wouldn't have to import it. It puts out less CO2. It still puts out some CO2.
Yeah.
You're still burning.
Yeah, you're not gonna-
I mean, burning would produce some carbon dioxide, definitely
I
some.
think it's in reduced levels. I don't know what, it's like an isobutanol, I think.
Okay.
It's iso something.
I don't know the details, I mean, what they would produce,
I
but
think it's isobutanol instead of ethanol, which is the difference.
well, yeah, we need energy is not going to last forever like this. We had our honeymoon time with energy, but now is the time where you need to start, taking caution. So, rest of the green chemistry principles. So, if you are using catalyst, then make sure you use the catalyst that allow the use of safe chemicals. Well, safety is the goal of green chemistry, right? That is why green chemistry, that area, people are looking into that. How safe we can do things. I mean, we've been experimenting pretty bad with all the chemicals we only created that. So now the goal is going to be everything safe. We don't want all those dangerous stuff. And try to use renewable feedstock as raw materials. Yeah, renewable energy is another big talk area, right? And another major point, try to reduce the amount of solvent used and try to use environmentally friendly solvent. Solvents are one of the big industrial waste we create, mainly the organic solvents, like all those acetone, benzene, all that stuff. Lot of processes, they need this big gallons and gallons of organic solvents, which just you have to worry about how do I dispose it now. They just don't deteriorate. They just don't disintegrate. And that is one of the main industrial waste we are creating. So reducing the amount of solvent, that is one big concern. And there are some talks going on, or people try using solvents such as supercritical carbon dioxide as the great green alternatives. Remember supercritical fluid. What is supercritical fluid?
Just gas and liquid.
It has the gas and liquid properties, right? So solvents, why solvents are used so much is they have great capacity of, as the name suggests, they have great capacity of dissolving a variety of things for the industrial processes. So the supercritical fluids, they also have the properties of gases and liquids. So they also can dissolve a variety of things. So if it is the only purpose of using that solvent is dissolving something to a great extent, why not find something which would do the same but doesn't have all the toxic effect, and you don't have to worry about how to dispose it. So carbon dioxide, supercritical carbon dioxide and supercritical water, those are the two great green solvents. Water, of course, we know that we don't have to worry about disposing pure water. Now carbon dioxide, the advantage when compared to the other industrial solvents, the other organic solvents, the carbon dioxide is very low if you look at the hazard level of the solvents versus carbon dioxide. And carbon dioxide, another thing is we are creating a lot of carbon dioxide as a byproduct in so many other processes. So why not just use that for this purpose rather than just, sending to the atmosphere and just making it worse out there. That is the other point. So yes, it's all out there, a big wide area. Still a lot of research and ideas going on, lot of achievements to come. Hopefully in our lifetime we would see some good improvements, right? Let's hope so. I guess that's the end of this chapter, guys.